Okay, so let us move forward from where we left in the last lecture. So, just to recall, the last lecture was about the Lee's approximation, which I did for 3-stage interconnection network, which was Claus configuration, and then of course we also did a cross point complexity of a Claus network. So, those two things we did, but Lee's approximation is not very precise. It has errors because we are approximating there. So, then of course I suggested that we can do more precise calculations, but this time not for time congestion, but for the call congestions. So, let us actually do it. We are actually considering here again 3-stage Claus network only, and we are going to, this approach is attributed to Karnaugh. So, it is known as Karnaugh's approach, and this gives a beautiful result about the call loss or call congestion. So, in this case the PL, in fact remember PB, when I am actually writing it is always the probability of switch being in blocked state. Whenever it is PL is a probability when a call arrives it is going to be lost, it is a conditional probability. Okay. So, PL will now be given as, so this we are not computing. So, PL we can write as, I will tell what this sigma is. Now, sigma is something which we have now introduced. This is known as, this represents the state of the switch. Now, what do you mean by state of a switch? So, if I have only one single switch, what are the states for this one? It can be either on or off, there are only two possible states. Okay. If I have a crossbar of 2 by 2, each one of them can actually be on or off independently. Technically there will be 2 raised power 4 possible states. Some of them are not valid states. Okay. So, in fact and some of the states will correspond to multicasting scenario. So, I am not looking into the multicasting scenario here, I am actually looking into unicasting case. So, there are many possible states which can happen. So, normally if the number of cross points are C, in general total number of states which will be there will be 2 raised power C, and of course which input and output are active will also be counted for. Here I am actually assuming that all inputs and all outputs are connected, they are actually communicating. So, under that possibility there are 2 raised power C possible states. Okay. So, this sigma represents this, but there is going to be large number of states, we need to actually take care of these. So, we use a concept of something known as equivalent states. So, what do you mean by equivalent state? If a switch is in one particular state, say A, and if it is in state B, the probability that you are going to be in A or probability you are going to be in B is same, the blocking which happens is going to be same. So, basically what you can do is, because switches consist of smaller switches, if I can move them around I can just do a renumbering, I can always go from state A to state B by doing this transformation. We will actually do an example of this while looking at a wide sense non-blocking switch and its proof. That time we will be actually doing this thing, then these becomes equivalent states. So, I do not need all these possible states to be taken care of when trying to compute this, I can represent it by much smaller number of non-equivalent states. We also go further ahead actually. Now, how this sigma can be represented, I am coming to that, but what does this P sigma actually means? P sigma is the probability that your switch will be in state sigma. What do you mean understand by lambda sigma? Lambda is the call arrival rate, number of calls which are arriving at any point of time. Okay. So, this represents that the call arrival rate probability you are in this state average number of calls which are arriving per unit time when you are in state sigma. Now this is conditional loss probability. When you are in state sigma, what are the chances that a call will be lost when it arrives? It is a conditional loss probability for an arrived call, and I sum it over sigma. So over a long range of observation period, this numerator will represent the number of calls which will be lost on an average, okay, because it is being now average over all possible states, taking care of the probability of being in that state, the arrival rates and the call loss probability. Now if you come back to the denominator, this represents the total number of calls which have been attempted. So this also includes the calls which were not lost, the total calls attempted, average over all possible states by using this probability, total calls attempted. So this is a ratio of the failed calls by total calls, and this becomes an estimate of call loss probability, okay, in general. Now question is how you will represent this sigma. So for doing this, I am going to actually take an assumption, which is known as we need to take assumptions. So one of them is random route hunting. Now the way it happens is, whenever you are going to have a switch which will consist of all these states, all these switches in 3 stages. Typically when a call has to be set up, the input and output ports are identified, then how the call will be routed? I will be taking up any middle stage switch and setting it up. I can do it randomly actually. So if I take another input ports and another input port here, I can take up any one of them randomly. So when a call has to be set up, the way the links are chosen, they will be taken care of, they will be done randomly. That is what the random route hunting actually means. I will just pick up randomly, will try it out, does not go through, I will make an attempt again till I get a free call. If it does not happen certain time, I will simply discard. It is possible I can always start from the top switch, keep on doing it till I find out a free link, set up the connection, everybody does that. So most of the time the upper middle stage switches will get occupied, lower one will not be. So that is an ordered system. Or maybe when I tried for the first call, I use this one, next one, this one, the call was through here, and when the next call will come, I will start from the next one. So that can be happening in cyclic fashion, but I am taking random route hunting. Advantage of this is I can represent the state of the switch by x and y. They are independent of how the calls are set up. At any point of time when I observe the switch, this is actually same, it is not changing. The earlier time history does not matter actually. So that makes it far simpler for us to do the analysis, and I can actually I need not take all the switches, I am only worried about only one of the input ports. So one switch here and one switch here we need to take. Now why we do it? And the number of links which are occupied here is x, number of links which are occupied here is y. But remember, I have other switches here also. So when I look at these combinations, so one input and this input output pair, that is independent of the earlier pair. For example, this AC which I was taking and BD which I am taking. So these are independent and they will be in the similar situation. So if I compute my estimate for AC, this is going to be true even for BD or any other possible pair. So I am also taking care of here, I am also making an assumption that it is a uniform kind of routing which is being used. So when somebody wants to make a call, it is going to make call to anybody else with equally likely probability. So it is a uniform loading condition. So under that condition, the sigma now can be very well represented by a pair xy, okay, and I need not bother about anything else but except one pair, so which is A and C here, and this number is x and this number is y, and x and y will represent the state. So, x can be 1, y can be 1, x can be 0, so all possible pairs, and they can take maximum values can be k, where 1, 2, the number of switches in the middle stage are k. Okay. Under this condition we have to compute. So, I can now modify my expression, this will become xy, xy and now I think I can compute. So, now if I draw this, so this one gives you x, this one gives me y. Probability of call arrival, essentially this technically means that or probability of xy, that switch will be in state xy, how this will be decided. X and y are independent. Why? Because when actually I am setting up the calls, all the calls which are coming emanating from this switch are not terminating here, they might be terminating here also, they might be terminating somewhere here also. So, this x becomes independent of this y. These outputs might get connected to the different switches via this route. So, y need not have any overlap with x, so they can be independently varying in this case. Okay. So, the probability of x and probability of y can be written as the product of probability being in x and probability of being in y. That comes because of the independence. Any two independent random variable, their joint probability is nothing but the product of the probability of each one of those independently, and that is what I have written. Okay. So, that is one important thing, we have to estimate what this px and py also. Now, next look at this plxy, how this will be estimated. So, you have a switch here, and you have 1, 2 till k, and of course these are A links and these are B links. And their x calls which are progressing here, their y calls which are progressing here. I have to find out the probability that call will get lost if I want to set up a connection between these free incoming and outgoing ports. So, this is a free incoming port, this is a free outgoing port. What are the chances that when you randomly select a pair, you will not be able to find out a path? Okay. So, that is comes from a Jacobius approximation, this is also known as Jacobius approximation. So, let us see how we actually figure it out. Now, if my x plus y, this is the x number of links which are busy, y number of links which are busy, if x plus y is less than k, if this condition is true, then what is going to happen? You will always be able to find out a switch. In worst case, x are occupied, y are occupied, and they are not connected to the same middle stage switches. In that case, you can always find out something for which A link and B link both are free, and I can use that to set up a path between from input to output. So, blocking will not happen if this is true. Blocking can only happen when it is x plus y greater than or equal to k. But then these x and y's are actually being the links which are occupied A type and B type are happening independently. We have to find out the chances that I may find out a path from input to output. Okay. So, let us see how this will be done. So, let me take an example. So, I have 3 links which are occupied, 3 connections, and in total we have 5. So, these 3 are occupied, 3 are occupied from this side out of these 5. So, these 3 can be like this. So, this is one possible combination. Now, you see that I cannot set up the path, set up a connection between a free incoming port and free outgoing port in this example. But as I said, we are using random route hunting, and this happens with the same probability as this. There is a path available, I can set up the connection. There is possibility that this will happen with the same probability. So, essentially if I freeze this, there are many possible ways this now can, these 3 connections can actually be distributed across these 5. In some of the ways you will find out you will not be able to set up the path, in some of the combinations you can set up the path. So, probability a call will be lost or you cannot set up a connection essentially now can be written as total number of patterns in which the blocking will happen divided by total number of possible patterns which can exist. Okay. So, this we can compute for this combination. Now, instead of this, if this would have been this scenario and I would have allowed all possible patterns here, I would have got the same ratio, it does not matter, it is the same case. So, I need not bother about x, so I will just fix it x and this is y. Now, the remaining balance will be k minus x, and out of this y, in how many ways this y actually can be arranged among these k middle stage switches. This will be k combinatorial y, that is a total number of possible ways you can arrange, in which you can arrange. And of course, now you have x occupied versions and k minus y unoccupied ones. So, k minus 1 y which are unoccupied ones, in how many ways they can be arranged across these occupied A links, that is the time when the blocking will happen. Okay. So, for example, when you have this possibility, these are blocked, there is another possibility this way, this is blocked, if you do this is also blocked. So, I am now trying to arrange the free ones across this busy stuff. So, in how many possible ways that can happen? Those are the number of blocked possibilities. So, if I take this ratio, so which will be x c k minus y, this should give me the probability that your call will be lost given x y. This is what is known as Jacobius approximation. So, I can solve this and we will get x factorial by k minus y factorial x minus k plus y factorial. So, in fact, I can write this as x plus y minus k factorial, and then of course k factorial y factorial k minus y factorial. So, this one will cancel and that is what will be the probability x factorial y factorial x plus y minus k factorial by k factorial. Now, you can actually see x plus y has to be greater than k, then only this makes some sense, otherwise blocking does not happen. Okay. So, this will be the expression which we can use it for PL given xy. Now, to find out that probability that x calls will be here, how to estimate this? So, you can actually go to some one of the earlier lectures where I have done m by n composite switch, where I have done the state probabilities for a m by n composite switch. Now here important thing is that you might have here certain number of inputs, I call them m, and this is actually k is here, so k is equal to n. So I can use same m by n composite switch result to find out px. So let us see how that will come. So instead of this m by n, this is now m by k switch. Okay. Okay, because my notes actually have n, so let me keep it n, and we will solve from here. At some point I will change the variables, I will do the transformation. For m by n, probability that this switch will be in state n, where n means outgoing n number of links are occupied, and remember in this case n is greater than m, okay, greater than equal to m, that is the case which we are looking at. So I can write down p of n, probability of being in state n outgoing links are occupied. If you recall from there, this will be mcn lambda by mu, lambda is the arrival rate, mu is the departure rate, or 1 over mu is the average call duration, okay, and this will be raised power n I can write any variable, let me put I, because we have been using there. Important thing, it was n mcn, sorry, this will be I. Now one thing which we need to note, that n is going to be larger than m, so this has to be changed to m actually, okay, and once I change it to m, because that is in the maximum number which you can get, you cannot actually have a state more than m. So this becomes a complete binomial. So binomial expression is mci a raised power I b raised power m minus I summation I goes from 0 to m, this will be always written as a plus b raised power m. So this is a binomial expansion, we can use this to solve this expression for Pn. So I can actually add here 1 raised power m minus I. So this becomes a and this becomes b, so a plus b. So 1 plus lambda by mu raised power m. Okay. I can actually further solve it. I can write this as lambda plus mu by mu raised power m, and I can take it up. So this will be mcn, okay, let me write it down at the bottom. So we can write it as mcn So I have just split it into m and n parts, the bottom one, mu raised power m minus mu raised power n comes here, lambda n comes here. Now mu divided by lambda plus mu is nothing but 1 minus lambda divided by lambda plus mu, and I call this as A. I will give the interpretation of it. What does it mean? It technically means loading of the telephone line or the line which is coming here at the input. Okay. So, if I do this, so this becomes 1 minus A and this becomes A, MCN A raised power n, that is what it will be, the probability of x Px. Now, whatever is true from this side, this is a symmetric system. So, the same should be true for Py also, okay, because technically when I am talking about Py, that is because of the calls arriving at all other input ports which are terminated at the outgoing line which I am currently observing, and that should be same as this is the input line and all outgoing lines to which this call is being routed. Px is because of that. So, both are symmetric systems. So, Py has to be equal to Px and they both are independent. So, I can write down Py also as MCN A raised power n 1 minus A m minus n. So, Px and Py we have found out. We have found out PL given x and y, which is this using Jacobius approximation. So, we have got this, we have got this, now we have to find out this, and we have to ultimately put it into the expression for getting my answer. So, in this case, now x lambda xy I was talking about, that is the call arrival probability. So, if I talk about the switch here, x links are busy, their total number of m inputs. So, what is going to happen is, how many input links are free here? It should be m minus x. So, the call arrival rate per line is lambda. In fact, I can call it lambda x. So, that will be the arrival probability. Similarly, on the other side, m outputs are there, one of them is free which I am trying to connect, links which are busy is y. So, how many are the free links available here is m minus y. So, this is the arrival probability here. So, I can write this lambda x as lambda x lambda y, this lambda x is this lambda y is this. So, I can write lambda x lambda y. So, this can be written as delta m minus y. I have also got my third term. So, I have to just actually now use all these three to compute my expression. So, let us write down the expression and solve it. So, P of L, so I have to write down summation, since sigma is equal to x comma y, I am going to put, I have to do summation over x and y. This actually means I need to do summation twice, with one with x and one with y. Okay. So, for the timing let me put it this way, at some point I will just put into double summation, or maybe now itself I can do it, it does not matter. So, sorry, this is, I am using gamma, so it will be gamma. Now, be very carefully, what I am actually doing is I am doing now transformation of variables. The middle stage switches here are k in number. Here the number of inputs are n, number of inputs are n. You have to be careful because I have used this small n slightly earlier and I am doing transformation, and n is now going to mean something else. Okay. So, it will be n minus x. So, this is just to be consistent with my notes, so that I do not end up in making some mistake. N minus y. While solving, we will also understand certain subtle things which we can observe in the process. So, this was MC something, so it will become NCX and then of course you have x factorial y factorial by k factorial and x plus y, this coming from the Jacobius approximation. Denominator will consist of, except PL rest everything will be there, and you can also observe why I was very careless about this gamma, because ultimately it cancels out, it is simply a proportionality constant, does not matter actually here. Yeah, I have made a mistake here. Okay, so now it is a correct expression. Now let us look at A. A I had written as lambda divided by lambda plus mu. What does it mean? So, on a trunk line or on a telephone line, lambda is the arrival rate, and remember I had actually mentioned in one of my previous lectures that lambda is because of the Poisson distribution. So, if I look at on time scale the events which are happening or the calls which are arriving, lambda calls per second which are arriving. So, lambda represents 1 over lambda represents the inter-arrival time will be exponentially distributed with mean value of 1 over lambda. So, the gap between two calls is 1 over lambda. 1 over mu simply is also in the same fashion. I had mentioned that 1 over mu is the call duration. When the call starts, it is going to be occupied for some time before the again the line goes free and a new call can come in. That call duration is also exponentially distributed with average 1 over mu. So, or we can say if the calls are being processed very fast, the mu number of calls per second or per unit time will be processed. Okay. So, because exponential distribution and Poisson distributions are interrelated. So, I can actually modify this and do the inversion. I can actually put this as 1 over mu divided by 1 over lambda plus 1 over mu. Okay. So, I can do this. So, once I do this, and this is nothing but as good as A, you can actually prove this one. So, this turns out to be same. So, this is on a time scale when a call arrives, this is the call duration. So, average duration for this is 1 over mu, and when the next call will arrive, that gap is 1 over lambda, and then the next call will be arriving. So, what I am saying is the busy duration divided by busy plus free duration on the line, that is what is A. So, A becomes technically a trunk utilization and its value will be between 0 and 1. Okay. This value will be between 0 and 1. So, it is busy period divided by period between two calls, busy plus free periods. So, that is what the A is. So, it is a line loading actually. So, let us now start solving it. So, we can see this gamma and gamma will cancel. So, that is very good. Let us see now what we have to do next. I can expand this NCX so that I can solve these n minus y and n minus x thing. So, let me do that. I can write as n factorial divided by x factorial n minus x factorial. I can do same thing for this, and same thing can be done here also. So, I can take this n minus x and n minus x factorial, and I can cancel it out. This will become n minus x minus 1. I can do the same thing with this. Same I can do on this side, but this is not a full combinatorial. So, let me take n out and make it n minus 1. Same I can take here n square. So, this n square can come out of the summation and can be cancelled out. So, this is what I am going to have. So, let us solve it further. So, n square I can remove from here, and what I need to have here is a raised to power x. Since this is a combinatorial which I am using, if I want to make it a full combinatorial sum, full binomial sum, it has to be n minus 1 minus x. So, it has to be n minus 1 minus x, it has to be n minus 1 minus y, which actually implies I have to take 1 minus a square out, which I can take out of the summation. It is independent of x and y. Now, these summations now can be taken, and I can put one summation here, and this becomes summation over y, and this becomes summation over, this is over y, this is over x. So, this summation now can be written as a plus 1 minus a raised to power n minus 1. Same I can do for this, and I can write a plus 1 minus a n minus 1. So, I can remove this one. This turns out to be nothing but unity, this also turns out to be unity. So, this is gone, and this is what we are left with. Okay. Now, solving it further, out of this, now writing it neatly, it will be 1 over 1 minus a square. This k factorial is independent of x and y. So, this can come out, I can write it here, rest everything I will still retain inside. N minus 1 factorial square can also come out. Okay. So, but rest everything has to be kept inside. So, I will have a raised to power x plus y. Yeah, this x factorial and y factorial will cancel from here. So, these will not be there. These have gone out. And that is what we are left with. Okay. So, we will now actually split it into two separate parts. So, what I will do is I will take a raised to power x plus y minus k. So, which actually means a raised to power k has to come somewhere here, I will put 1 minus a n minus 1 minus y here. So, I need to take somewhere here 1 minus a n minus 1 minus x. This is because this 1 minus a square has to come up. So, that these minus 1s are sitting in. So, I have to remove this. Okay. We will also add a factorial here, so that we can solve it later on. N minus 1 plus x minus k. So, I will put the same thing in denominator here. And I will keep this n minus x. So, I will take this part. Now, you can see there is no, the x is something which is the in this summation. So, I have to solve this thing first with respect to y. Okay. This is a complete binomial. You can actually add these two, a and 1 minus a. This turns out to be n minus 1 minus y will cancel with this, n minus 1 plus x minus k, n minus 1 plus x minus k. Okay. X plus y minus k is here, n minus 1 minus y is here. So, this forms a binomial actually, but what is the range of y in this case? So, that is one of the interesting questions. So, range will be when x plus y minus k, because this is something which has to be certainly observed. Otherwise, you know, it is a binomial, I can simply solve it by adding a plus 1 minus a raised to power something. Okay. So, when x plus y minus k is 0, that is one possibility. Okay. Secondly, this can go from 0 to the largest value, which is this one. So, second possibility is that x plus y minus k will become equal to n minus 1 plus x minus k. In this case, the k will cancel, x will cancel, y will be equal to n minus 1 is the range here. So, y will be, so y will range now n minus 1 coming from here, and y will be equal to k minus x, sorry. So, in fact, you should note here, if y is not greater than k minus x, switch cannot be in blocking state. Switch can only be in blocking state when it is greater than k minus x. Remember, when this is we did while estimating the Jacobius approximation. So, this is the range in which y will be valid. So, this range has to come here in the summation, and this forms a complete binomial. So, complete binomial means this plus this, a plus 1 minus a raised to power whole term. So, I can represent, I can actually rewrite it as a plus 1 minus a n minus 1 plus x minus k. So, this is 1 raised to power anything is going to be 1. So, this is immaterial, this goes away. Only thing which remains is summation with respect to x, and I can rewrite as this. In this case, I can actually sum these two things up and make add a factorial here multiplied by that. I should now remove this one. this will be 2n, x will cancel, 2n minus 2 minus k, that is what it will be. So, I have to divide also. So, but this is independent of x, so I can write it here. Now, here x will be actually also going taking up a range. So, x can take now a raised power k is going to come out, which is the second term here, 1 minus say this. So, 1 raised power something is the second term. So, that second term is 1 raised power 2n minus 2 minus k minus this, actually it will be n minus 1 plus x minus k. Okay. Now, this forms a complete binomial. So, what is the range of x here? So, when n minus 1 minus x goes to 0, so x will be equal to n minus 1, that is one possibility. Secondly, when this term will go to 0, which is n minus 1 plus x minus k. So, k is equal to n minus 1 plus x. So, that is going to be the range in which it is going to operate. So, this also becomes a full binomial. I can replace it by one plus 1 minus a 2n minus 2 minus k. So, which is gives me the expression for P of call loss. And remember, this can only give you a value if you are going to have k less than twice of n minus 1. Okay. If k is less than that, then only it will make sense, otherwise it will not. And of course, one important thing is, this is the call loss probability. There has been another approach by which a computation can be done for the switch being in the blocked state. Okay. So, I have not done that here, and if you do that, I will end up in a expression which will be PB, which will turn out to be a raised power k, and it is an interesting expression. It will be n factorial square 2 minus a 2n minus k divided by k factorial 2n minus k. And you can actually clearly see the relationship still holds. The relationship which we had, that PB n minus 1 this relationship which we have derived earlier also holds true here. Okay. So, that was the method of estimating the blocking probability using Karnaughs approach.